Welcome to the first tutorial video for the ITensor library. In this lesson, we'll discuss the basics of tensors, but won't yet discuss any code until the second lesson. By a tensor, a good starting point is to just think of a very pedestrian definition, which is that it's just a box of numbers indexed by some number of indices. So what we mean is that it's a generalization of a vector, which is a set of numbers indexed by a single index, or a matrix, which is indexed by two indices. And so a generalization of this would be a set of numbers with three indices, which we would call a rank 3 tensor, and so on. A rank 4 tensor would have 4 indices, and we can make higher and higher generalizations. Now, this is not really a very mathematically complete or satisfactory definition of a tensor, but it's a good way to begin just to get an understanding of what the ITensor code is doing and how it works with tensors. For a more mathematically complete perspective on tensors, one can think of them as actually multilinear functions of vectors. So for example, a matrix, instead of being a box of numbers, is actually a function that takes in a column vector and a row vector to produce a scalar and is linear in each argument. For more information about this perspective, you can see the excellent book by Nadir Javanji called An Introduction to Tensors and Group Theory for Physicists. Now going back to our examples of tensors, there's a much nicer modern way to notate tensors which will be used extensively throughout these tutorials, and that's called tensor diagram notation. So what's on the left is called traditional or classical tensor notation, where a vector is named by a letter and its indices are written as subscripts or superscripts and are also given names. So in this case, a vector has one index called j here, and j can take the values either 1 or 2, in which case we get the first or second component. Now in tensor diagram notation, we denote the vector instead as a circle or a blob of some shape. Here it's the blue circle, and because a vector is by definition a rank 1 tensor, we denote its single index by a line coming out of this tensor. Now we've already given this index a name, j, so we can also put the name at the end of the line. So similarly, a matrix is a rank 2 tensor, so it's a blob with 2 lines coming out, and here's our rank 3 tensor with 3 lines coming out. One advantage of this tensor diagram notation is that we don't necessarily have to think of names for all our indices. So we can just omit the names, and we can tell a matrix as just any blob that has 2 lines coming out, or a vector as any circle that has 1 line coming out. So similarly to classical notation, just as we can think of j taking the values 1 or 2, we can think of our line taking the values 1 or 2. So we could think of setting our line in our diagram to the value 1, in which case we retrieve the first element of our tensor. Or we can set the line to the value 2, and again the diagram becomes a scalar having value 3. A more complex operation we can do with tensors is to contract over their indices. What this means is to hold some of the indices at having fixed values, fixed but arbitrary values. In this case, we hold the row index of this matrix as having a fixed but arbitrary value I, and then sum over other indices with products of other tensors in the sum. So for instance, this complicated looking sum is nothing but taking a matrix, here with indices I and j, and multiplying it by a column vector, here with index j. This is also called contracting over the column index j. In more modern tensor diagram notation, we don't actually have to write the summation symbol or the names of the indices, but instead, the summation is implied whenever we join 2 common lines between 2 tensors. So here we join one of the lines, which is the column index of the matrix, with the single index line coming out of this vector, which implies that we now sum over all the values that line can take. The other line is not contracted, is not joined with any line from another tensor, so it's assumed to be held to a fixed yet arbitrary value. Just as a final quiz of this tutorial to make sure that you understood that discussion about contractions, let's take a look at 3 example diagrams and think about which common matrix and vector operations they correspond to. If you need more time to think about it, pause the video. Okay, here are the answers. So the first diagram corresponds to a row vector. We can tell it's a vector because it has a single index line coming out, contracted with a column vector, which is more commonly known as the dot product of two vectors. The second diagram corresponds to the product of two matrices. We can tell these are matrices because they both have two index lines. And the final diagram corresponds to multiplying a matrix times a column vector, and then taking that result, which has a single index, and contracting that with a row vector. So it's a row, matrix, column contraction. One interesting thing to observe about tensor diagram notation is that it immediately helps us to see what kind of product results from a certain diagram. So for instance, the first and third diagrams both have no external lines left over, so these are both diagrams that reduce to scalars when they're fully contracted. The second diagram has two external lines, which tells us that the result is a matrix, which we know is right. When we multiply two matrices, we get a matrix. Okay, thanks for watching.